Diana. So our speaker this morning is Dr. Diana Yousef, the founder and CEO of Changewater Labs. Diana is a biochemist and sustainability innovator who has spent her career working at the intersection of science, public policy, and global development. Before founding Changewater Labs, she worked with organizations including the United Nations, the World Bank, and the International Finance Corporation, focusing on ways that technology can address real-world human challenges. Diana holds a PhD in biochemistry from Cornell, an MBA from MIT Sloan, and a
Oh no, actually not MIT Sloan. Whoops. ChatGPT. Okay, no. No, I have, biochemistry degrees from Harvard and Cornell, and then MBA and Masters in International Development from Columbia.
At Changewater Labs, she leads the development of a new kind of waterless sanitation systems that use NASA-derived material science to safely evaporate wastewater on site. This allows communities without sewer or plumbing infrastructure, including refugee camps and remote, climate-stressed regions, to have access to private, dignified sanitation where it has never been possible before. Please join me in welcoming Dr. Diana Yousef.
So hi, I'm Diana Yousef. I'm the founder of Changewater Labs, and our team has invented a technology that can enable the evaporation of human waste. So a few years ago, I was consulting to NASA looking at how to recycle wastewater on the space station. And what I realized is that just like in space, there are a lot of places on Earth that don't have great ways to get rid of sewage. So as a matter of fact, 4.2 billion people, that's half the people on the planet, live in places without safe toilets, and that's because they don't have access to hookups to water or sewer plumbing. So they can't flush away their waste. Additionally, 80% of human sewage is dumped untreated into the environment. So that's the equivalent of, well, so actually, and that also includes the US, which dumps 1.4 trillion gallons of sewage into our waters every year. So that's the equivalent of every American dumping 12 gallons of sewage into our waters every day. So poor sanitation has such an outsized impact. It poisons people and the planet. It causes 80% of all infectious disease spread and 4% of all deaths globally. It also causes a third of nitrogen pollution into our oceans, and that in turn causes mass die-offs of marine life, fuels dangerous algae blooms, and also is smothering 2/3 of our coral reefs. It also contributes some of the worst greenhouse gases. So that includes methane and nitrous oxide, which are 30 and 300 times more harmful than carbon dioxide. So billions of people will never have access to sewer sanitation. With explosive urban growth, coupled with the lack of proper infrastructure expansion and increasing water scarcity, about 1/3 of people living in cities will have to have a non-sewer toilet. That's 2 billion people. And that also includes coastal communities. So the densest populations on Earth are cities and coasts, and increasingly they're going sewerless. So the private and public sectors already spend $19 billion per year on non-sewered alternatives for toilets, but none of those will keep communities clean or curb climate change. And when you can't flush, especially in crowded communities, things get messy really fast. So waste has to be collected like garbage, which is costly, messy, and not sustainable. So the idea that I had when I was at NASA was for a toilet that makes waste literally disappear. No flushing, no frequent collection, no dumping, discharge, or pollution. The key insight is that human waste is mostly water. It's about 95% water. That's like 100% of urine and 85% of solid. And instead of flushing that water, we could just evaporate it. So looking to nature as the chief engineer, or the smartest engineer around how to move molecular water, we took inspiration from a process called evapotranspiration. And that's how plants move molecular water from a wet area to a dry area. So basically plants, when they soak up sunlight, they sweat and they release molecular water through pores on their leaves. And then this evaporation of water from the leaves drives absorption of water from the wet soil below. So essentially what you have is this movement of molecular water that's driven by this moisture differential between the dry air above and the wet soil below. So taking the inspiration from both nature and space, we've developed a product called the iThrone. Rapidly shrinks human waste. The iThrone uses bags made of a novel material that we've developed that we call shrink wrap for crap. These bags will soak up the liquid water content from waste, and then by pulling it through the membrane, will convert that liquid into pure molecular water vapor. So it's basically like evaporating, but without needing heat. So as a result, the iThrone is able to get rid of 95% of daily collected waste through evaporation in just one day, and by rapidly dehydrating waste before it starts to convert into greenhouse gases, it can eliminate the emission of greenhouse gases from unflushed waste. Additionally, our toilet separates the waste streams, and the dried waste products can essentially be used for conversion into organic product like fertilizer, bioenergy, biocement, the basis for animal feed, etc. So the iThrone gets rid of human waste fast without water, flushing, pipes, or pollution. It's because it doesn't need hookup to water or sewer, and because it shrinks the waste so drastically every day, it's easier and cheaper to install and service, and it's also cleaner for the planet. So when you look at the iThrone compared to other alternatives that you all might be familiar with, the iThrone is really the only toilet that checks off a lot of boxes for crowded communities. It basically doesn't use water, it doesn't discharge waste into the environment, it doesn't need a lot of energy, it doesn't take a lot of cost to operate, and it doesn't need frequent collection, and it doesn't discharge waste into the environment. So it's really the only toilet that makes waste literally disappear. So we think that the iThrone is going to be uniquely positioned to address the growing problem of lack of flush toilets in urban areas. So it can be a clean, compact drop-in solution for non-sewered urban areas, and also a waterless solution for dry conditions, a drop-in solution for emergencies, and also a non-discharge solution for coastal communities. So we've run 2 pilots over more than 2 years. Our systems have serviced more than 16,000 uses, and the data that we've gotten has shown that the iThrone is actually getting rid of 97% of daily waste collected in the toilets every day. They can run 100% off-grid because they don't need hookup to water or sewer. They're about 500 to 300 times cheaper to install than comparables. And while other container-based sanitation systems have to be actively emptied, and that's usually every 1 to 2 days, we're running the iThrones 1 to 4 months before we have to empty them. So that's pretty transformative. So it's really a solution that has an outsized impact. So I don't know, people know what the SDGs are? No, Sustainable Development Goals. So these are the global agenda for how we're going to essentially equalize the playing field for everybody on Earth, economically, socially, and environmentally, are these what are called the Sustainable Development Goals. And normally, sanitation solutions will solve SDG 6, but we actually think that we're addressing 13 of the 17 SDGs. In a year, a single iThrone has the ability to reduce disease exposure for 1,000 people in the surrounding area, conserves 1,000 bathtubs worth of fresh water, eliminates 1,000 bathtubs worth of fresh water per year, eliminates 24 bathtubs worth of sewage every year, and cuts off greenhouse gas emissions equivalent to burning 125,000 pounds of coal per year. So in our next deployment, we're going to be deploying 100 units of our iThrone porta potties to Santa Fe, New Mexico for a homeless housing project. If you ever happen to be around Somerville, we've built a demo unit in a climate chamber at Greentown Labs, which is where we work out of. And we've already had $750,000 of paid contracts and inbound interest and LOIs for 6,000 units from essentially the private sector and the public sector. So that includes construction firms that are interested in permanent non-sewer toilets in non-sewer developments, alternatives to septic that don't discharge waste, lower cost, lower OpEx porta potties, and for the public sector, emergency and public sanitation that's cheaper and easier to install and service. So we have a team that brings together 50 years experience in clean tech innovation, manufacturing, hardware engineering, sales and marketing, venture capital, and international development. And all of us have this aim to get safe and sustainable sanitation to more people in more places at lower cost. And I brought a little shoebox demo of the iThrone just to explain what this is. So this is how it works. These bags are the shrink wrap for crap material that are evaporating the water in these waste waste deposits. Essentially, what it's doing is it's the combination of the membrane and a fan that's pulling air into the system and pushing the humidity out of the system. What you see here is over time, there are load cells in there's like weight sensors in the little demo that are showing how it's evaporating. Basically, the system's getting lighter because we're evaporating the water. And I also have a little demo of the shrink wrap for crap material. I guess I can try to see if I can show it. I don't know if it's going to show up on your camera and if you guys are going to be able to see it. So if I put like liquid water on, I don't know if you guys can see it. It's sort of, let's see, how do I do this with multiple hands? Okay, so basically what happens is the material will swell up where the liquid water has come into contact with it. And then if you look at it in a couple of minutes, you'll see that the spots of water, it's whitish I guess the sunlight isn't helping, but where it's swollen, you'll see it'll actually be like going back to its original form because it's evaporating the water. So maybe if you want to come up and play with it, you can. You need a couple minutes to see the phenomenon, but it's pretty fun. So anyhow, I'm happy to answer any questions. There's no problem with toilet paper. I mean, it's essentially a solid that you can't evaporate away. So yeah, it just adds to what's being deposited into the solid bag. So yeah, it makes it fill up a little bit faster, but it's not a big problem.
How is it different from a composting toilet?
So composting toilet's trying to drive a metabolic conversion of waste in a way that kills the pathogens. It doesn't do anything about eliminating the waste volume. So it doesn't shrink the waste volume, right? And ideally what you try to do is you try to shunt liquid into a different direction. Usually most will actually just divert the urine into the ground. And then the solid will be in its own collection. And then you're trying to drive an aerobic or an oxygenated like metabolic process, which is not easy to do because what it requires is you have to like frequently feed it carbon and you have to churn it to get oxygen. So all you're trying to do is get rid of pathogens. You're not shrinking it. And so the difference with our toilet is that we're literally trying to drastically reduce the volume on site. What that does is because you're depriving the microbes of water, they stop metabolizing so that they don't convert things into methane and nitrous oxide. They don't convert into odor. But also by depriving it of water, you're also killing off a lot of the microbes. I won't say that what comes out is hygienic, but I mean, because we're not actually trying to kill the microbes, but it's a side effect of rapid dehydration. So so basically, the answer to your question is composting is trying to inactivate pathogens by driving an oxygenated pathway of metabolism, but it doesn't shrink the volume on site. Ours is a waste-reducing toilet that drastically shrinks the volume.
Yes, can you talk a little bit about the installation and how complicated it is or not?
Yeah, the installation actually isn't too hard. So what we did with the Panama toilets, sorry, let me get back to that. Yeah, sorry, you have to go through my whole storytelling. Okay, yeah, that's those systems on that side were installed for residential toilets in Panama. We just sent the designs for the cladding, the box basically, to the construction company that was partnered with us on this pilot. They sourced the basically what looks like an IKEA toilet and built it. And then we just came down with the ventilation package and the bags. So it's not too hard. I mean, essentially the way that we're planning to scale up to the market is either have like a fully integrated injection molded toilet that gets shipped kind of like a dishwasher or refrigerator, or out-license the design to, either construction company or some kind of company that has the ability to source the, essentially the panels and the frames, and have them install the toilets, and then we just send them the ventilation packet, which just gets plugged in, and the bags. So yeah, shouldn't be too hard.
When you say plugged in, does it need electricity to operate?
Yeah, it needs a little bit of power. So we run these. So actually, what was interesting about Panama was we were really worried because generally Panama is like 90% humidity on a daily basis, and so we're trying to passively evaporate water and into sopping wet air. And we thought, so we oversized the toilet thinking if we're lucky we'll get 70% evaporation efficiency, and we thought we had to run the fan at like 100%. Turns out that we're getting 97% evaporation of the waste that goes into the toilet, running the toilet at 0.2 kilowatt hour per day. That's about 1/10 to 1/20 what the ventilation power for a composting toilet is. So it's solar. So it's actually the red toilet runs completely on solar. The blue toilet's hooked up to pirated grid. We don't ask questions. I mean, that's how people live. But it goes down quite frequently. And so what we've done is we've made sure that even if you don't have ventilation through the toilet, you don't get odor in the bathroom. 3 ways. One is, so normally the ventilation, essentially ventilates the toilet. 2, the rapid dehydration essentially cuts off odor production. But 3, we have an organic coating that we put in the bags, and that helps to outcompete the growth of the odor-forming bacteria, so that even when these systems are down during a brownout, they don't smell. So yeah.
Could you talk about kind of how fast it's able to work? And, so I guess the thing that comes to mind is, just how robust the toilet is. To put in public space, can people be constantly in there through the whole day and keep up okay? And then even at 95 or 97% evaporation, it's not no waste.
Yeah, you can't get rid of 100%. Yeah.
Well, if you talk about a ton of waste, you still have, over tens of pounds left. So where does it go?
So I'll answer that in a second. Do you have a tech issue?
I don't think the mic is going to be picking up some of the questions.
Oh, do you want me to pass them? Oh, okay, sorry. So, okay, let me see if I got. So the first part of the question was, sorry, repeat the first part of the question. Yeah. So what's the throughput on the system? And the second part is, what do you do? Like, what do you do with the remainder? Okay. So we spec these out to accommodate 50 uses per day. So that's, yeah, we're going to see what happens when we send them to New Mexico, because we want to see how high the throughput will be, or how high throughput it can accommodate, but essentially 50 uses per day. So that, so basically 50, so it's basically, that would be accumulating 15 to 20 liters of waste, and then we get rid of the majority of it. We pretty much completely dry it. So yes, you can't, there's certain parts of waste you can't evaporate. I mean, that's just the fact. But if you're not going to be flushing it, then the next best alternative is to just shrink it as much as you can. And then while like a typical porta potty or other types of container-based toilets, they have to be emptied every 1 to 2 days, because you're not getting rid of any volume and they fill up pretty quickly. And the mix of solid and liquid is pretty unpleasant and dangerous. We're shrinking it and stabilizing it. So essentially, you can't, I mean, there's just certain laws of nature that you can't get around. Like there is some, I mean, we eat solids, like we don't live on a completely liquid diet. So there is going to be some solid, but it has to be collected. But the operational efficiency of going from emptying a toilet every 1 to 2 days versus once a quarter is pretty transformative. So yeah, we can't do anything about, what you all eat, but yeah, it has to be, but it's, I mean, it's not even marginally better. It's like I mean, it'll be solid, so you probably have to dump it into, you probably have to, dump it into the solid plant. I mean, it's more like your municipal solid waste, except that it's,
So
waste.
going to similar streams.
It could be. I mean, the way that we're dealing with it in New Mexico, they're deciding between either incinerating it or putting it or composting it. So we were talking to another company that's got sort of more sustainable porta potties in Cape Cod called Wasted. For them, they're landfilling the solid waste. Their waste is still fully wet. So yeah, I mean, so what, if it all depends on what the rules are in the sort of like the regulatory environment that you're operating in, where the servicer is operating in. So if they're allowed to do something where they circularize it into compost or bioenergy or fertilizer, then that's great, because this completely lends itself to that. But if they have to either get rid of it by incinerating it or landfill it, it's still better than what they would do with the alternative, like 95% water waste. I mean, in all these processes, essentially, the real problem is the amount of water in the waste. The other thing that, just to think about it, like if you think of a beverage company like Coke, they don't ship Coke to you. They ship a syrup to you, and then they add water at the point of distribution. We're sort of the opposite. We get something that's mostly water at the point of collection. We get rid of that water, so all the logistics and downstream processing or disposal is just much cleaner, much more efficient, much more sustainable, and much less. Yeah. Did that answer your question?
Yes.
Yeah.
And all the nitrogen and phosphorus is left in that solid material, right?
So we have that layer that I told you about that outcompetes the odor-forming bacteria, also stabilizes the nitrogen, and all of the phosphates would be inside. I mean, everything that's not water is still inside of the bag. So we don't get. I mean, so we have to test it, but we're essentially that we know that additive that we put in reduces the conversion from urea to ammonia. So it stabilizes it so that if it was, you want to use it for fertilizer, there's more of that nitrogen available for that. Is that what you were asking? Yeah.
So in situations here on the Cape, oftentimes you have a pond and the community around the pond, and almost all the homes have septic systems that are going to have to be upgraded in the near future, hopefully very near future. And so I'm thinking that the nitrogen problems we're having in the ponds and that sort of thing would be eliminated by this if a home can, when they have to convert their system into an upgraded system, if they convert it into this, the only overhead, or whatever you want to call it, would be that they have to get rid of the solid waste.
Right.
And in that case, would the cost of
I think
creating
so.
a
Yeah.
collection system, maybe like a garbage collection or whatever, in the community, totally be offset by the savings of not having to convert to
Right.
the newer septic system,
Right.
which might get rid of part of the nitrogen.
Yeah, I think so. I think I get the question. So basically, what you're saying is, is this potentially an alternative to septic that solves some of the problems that you all have here on the Cape? And does the trade-off with the cost of servicing the system, which is probably more frequent than a septic system, does that sort of, does that obliterate the benefit? So right now in its current form, I mean, we're not at scale yet, so probably, so the cost of getting one of these is about $8,000, but we're trying to get down to, between $800 and $3,000, depending on how sensor enabled the system is. So how smart the system is. And that's the toilet, right? I think probably for the Cape, you're probably more interested in a septic version of the system, so more like a receiving tank that then does the evaporation and doesn't allow any discharge. So, and that's a little bit similar, more similar to what we deployed in Uganda, which basically these were squat toilets, which is more, I don't know if you've ever used one, but that's more appropriate for public toilets in certain countries. And so that just literally sat underneath, it just basically received the waste. So it wasn't like something you sat on. So, we are looking at the conversion of our technology into essentially like an evaporative tight tank, and to receive the waste and evaporate it. As far as so from what I understand, these IA systems cost about $50,000 to $100,000 to install. If we were selling this, between depending on where we land with the technology, once we, outfit it, 3 and 10, and then the quarterly, replacement of the bag. Right now we're targeting, $25 a bag. So I guess you could do the calculation and see whether that makes up the difference between the $50,000 and $100,000. Yeah, it's probably cleaner too than some of these IA systems. Yeah. So I don't know. Was that a satisfactory answer?
Is there any, are there any initiatives to try to do something on a personal home basis on Cape Cod?
We've been talking to a lot of people, and so I think if we could find a partner to help us, like essentially fund that kind of product development and conversion, we're in Massachusetts. We want to find a way to do this. We've actually had there was supposed to be a pilot in Barnstable of the porta potty version on a beach. And we got blocked by the Massachusetts Plumbing Board, who said that they had some authority over portable toilets. And so there's a little bit of protectionism that we're having to battle. They keep wanting me to go and get their approval. And I'm like, nobody else has to. But for a built toilet, that's a different thing. I think we have to do this Title V approval or this IA thing. The Mass TC is pretty interested in doing something with us. We've had a bunch of inbounds, but we just need help with kind of funding it and sort of having the bandwidth to do it. Right now our first priority is to get that porta potty version out to New Mexico. But we'd be really interested in at least getting a couple porta potties running on the Cape if we can. What I'd really like to do is maybe something like a high usage pilot, like maybe at the ferry station in Falmouth or something. I think Barnstable, we just don't have a chance to do it because they're stuck on, making us go through this unnecessary process with the Massachusetts Plumbing Board, and I'm not going to do it. So, yeah.
There are plans for in the year 2030 or around then to put in new septic treatment systems.
Mm-hmm.
That's going to be quite expensive.
Yeah. No, we've heard about it, and I think so. Yeah. So we're at a stage where we're also raising money for our next phase to sort of essentially be able to scale up the manufacturing. We want to help solve this problem. We just need the right partners and some funding. So yeah.
Do you have any leads on who the right partners might be?
I think, my guess might be construction companies or companies that essentially do these types of systems, funders, obviously, municipalities. I think it could be kind of a sort of constellation of partners, but yeah, right now we just don't have the funding to do it, but if somebody wants to sponsor it, we'd be keen. So, hey, Talitha.
Thank you for this. So I help homeowners build accessory dwelling units in the lower and outer Cape. And it's really hard to build them because of wastewater challenges, specifically the cost of IA and the weight of the sewer. And so I've been looking into alternatives and kind of the umbrella of looking at non-sewer sanitation technology like this has been really interesting to me. So I'm actually leading a regional working group of 8 towns, municipal leaders and community citizens interested in housing and wastewater, innovative wastewater, is starting this month. And so I would love to be able to share some of this, because I think one of the ways to pilot is maybe with ADUs that are new builds, that are smaller builds, that get people housed, new people housing, right? And that's the thing I'm really kind of excited is to see this new technology that's based in our own state, to see how can we, besides a beach porta potty, think about it as a housing tool.
Yeah, so to repeat the question or the statement is, maybe ADUs and this working group of 8 municipalities might be a good partner to try to figure out how to get these systems tested and deployed for the issues in the Cape. We'd love that. I mean, it would be amazing if we could do something in Massachusetts. I mean, we've run up against these weird regulatory things. I mean, we're a category creator, right? So, and the regulatory agencies keep trying to put us into like the old legacy regulatory frameworks. And then, of course, this Mass Plumbing Board thing is just a protectionist move.
Can I add a little context?
Yeah, sure.
Here? So the Cape is leading the country on these issues of innovative toilets. And they are looking to us to figure this out for most coastal communities, most water scarce communities in Santa Fe. And so the people in Falmouth are leading the way. I'm hoping it's not just Falmouth. Like, I'm from Harwich, and we were the town in the 80s that did the solar aquatic innovative wastewater pilot. Like, we have led the way on this little sandbar in multiple ways, including a toilet on this campus, right?
Yeah.
So that's where I get really excited about piecing all those things together. But Mass Tech and the people involved in the Falmouth pilot are doing a lot of great regulatory work, but it's really hard. There's some definite hurdles with the DEP, the plumbing board.
Right.
But I think the more that people see this is not just about a watershed tool, that it's a housing tool, it's an economic development tool, it's a water
climate change mitigation, all of that. Yeah.
And we're a great community to show all of those different ways that this is also a climate, tool. So
I mean, there are a lot of gaps in sort of looking at wastewater. I mean, when you talk to people in climate change, it's taking them a long time to realize that water and wastewater are contributors to climate change, not just symptoms of climate. I mean, and as we're both biochemists, right? And like how people don't get it, that like clean water isn't free. I mean, it takes energy, and when it's dirty, it's emitting stuff. And it's just, it's been an uphill battle just to get people to recognize that this fits within the whole climate change puzzle. And then on top of that, and I have to sort of iterate some of the things you're saying, where we wouldn't exist without some of the visionary funding from the Mass Clean Energy Council and MIT as well. I mean, I'm not from MIT, but we got integrated into MIT. We got some real generous support from MIT in the early days when this was just a concept in my head. So Massachusetts has a great way of stimulating visionary, global, game-changing solutions. And then you get to the point where you're trying to deploy it, and Massachusetts and California are going to be the last states to get it because it's so hairy. And I don't have the time as an innovator and somebody trying to survive, because guess what? Shocker. Toilets are not a great asset class for venture capitalists to invest in. Gosh, who would have thunk it? And so so in any case, I'm being told to go ship these to Vermont, ship that, New Mexico, all sorts of other places. But, so we got to figure out how to get it together in Massachusetts, because innovative companies leave Massachusetts because of this. So is that a tech thing or no? A question. Okay. Yeah.
When we talk about wastewater and the elimination of certain chemicals, or not chemicals, things like nitrogen and phosphates, our generation is the most medicated generation of any generations before us, right?
Mm-hmm.
We have medications for immunosuppressant drugs.
Right.
Right. So, not only do they immunosuppress your body, but as you're releasing it via urine or whatever.
So is the question,
what did you?
Yeah. So okay.
Where birth control.
Yeah. So all of that will stay inside of our bags. That doesn't get across the bags. Now, so what you would want to do is take what comes out of the toilet. So it's not ending up in the water, it's not ending up in the ground, it's staying contained in the dried waste in the bag. And then what you do with the waste afterwards will determine whether it ends up recirculating into, you know, the environment. Like if you dump it, then yeah, that's not great. If you compost it and you do it properly, where you essentially, supposedly composting, if you do it properly, the compost will essentially heat up to the point where it should be breaking those things down, or you could incinerate it. Yeah, so it would have to depend on what you do with the waste afterwards. We don't, like, literally, our system does one thing: it subtracts water. And so, but it also just doesn't let anything into the environment. So it depends on how you manage the collected dried waste afterwards.
Are the waste treatment plants today,
Huh.
do they deal with this situation?
I doubt it. I don't think so, because it's essentially, they're mostly membrane bioreactor systems that just, most of what they're trying to do is eliminate the pathogenicity of the waste. So essentially they put the waste through essentially a brewery where microbes will eat the waste products, but they don't metabolize the pharmaceuticals. So that stuff just gets recycled. Yeah. I think maybe somebody here is more of an expert. Yeah.
Well, in terms of the urine, this is my
Yeah.
question with you, separating them out,
Mhm.
evaporating it, because what is amazing about MassTech is they have the technology right now on site to take urine and pasteurize it and filter it, so that PFAS, like, they're doing way better at getting rid of this than what you would put through the sewer.
Mhm.
And what they're doing that for is to then turn it into fertilizer. And the weird thing about our state is we have the end product of fertilizer being approved by MDR.
But no urine diversion.
But no fixture
Yeah.
to collect it and process
Yeah.
to get to the fertilizer.
Yeah.
So we kind of are backwards at this point. But they've approved it as 3 different fertilizers derived from urine, both a powder form and a liquid.
Mhm.
So if we could collect the urine from this type of toilet and pasteurize it at MassTech, we actually have fertilizer as an income, a second economy. Instead of trucking nitrogen and phosphorus over the bridge, we could be making it and either trucking it back and someone paying for it,
Yeah.
or figuring out a way that with our protected aquifer, we can use that in a safe way.
And in for every process where you're converting waste into something, the very first step is dehydrating it. So we do it at point of collection. But yeah, I think I talked to Brian Horsley, and I assume, I've heard that they've gotten some funding to do this research, but they don't know how to onboard the funding, because basically by doing the research, they'd be breaking the law. So it's,
Toilets need to be approved by the plumbing.
yeah, urine diversion is not allowed in Massachusetts.
If you were to point to an object, if I said to you, what would one of these take up, how much space would it take up in my home? I just point to an object around here to give us an idea.
A little smaller than this table right now. I mean, we could probably make it smaller. We'd have to think about but again, I mean, I think probably the product for the Cape eventually is going to be a septic tank that, you know, so you don't have to worry about the size of the septic tank. Really, in that case, what we'd have to figure out is how do you actually convey the waste from the bathroom to a tank? Because right now we're just using gravity. But yeah, I think about that size. We could probably make it smaller. The reason we made it that size is because we wanted to see how long we could go. First of all, we thought we were only going to have like very limited efficiency with the high humidity, but then, and we turned out not to. But then we also just wanted to see how long we could go without servicing, because the challenge we thought was going to be the cost of the servicing and the frequency of it.
When composting, do you have to remove the membranes?
So 95% of what the bag is made out of can go into the compost, and there's just one easily separable layer that's not.
2 questions.
Yeah.
I love the water reduction, the environmental aspect of that. Is this also a waterless toilet?
Mm-hmm.
Okay, that's awesome. And
Yeah.
2, you're talking about the downstream waste.
So just to repeat the question for the camera, I guess, is the question was, is this a waterless toilet? Yeah, it doesn't hook up to water. It doesn't hook up to sewer plumbing. So yeah, it doesn't take any water. Yeah.
And then the second question is the downstream. I hear a lot of people will throw away things that aren't supposed to be flushed,
Mhm.
things that are supposed to be considered biodegradable but aren't cleared biodegradable. Is that all kind of a secondary problem for the downstream processing?
Yeah, I think, yeah, because actually what we're thinking about, so the question was, who deals with the issue of things that are not human waste getting thrown into the toilet like trash? Yeah, that's, yeah, is that a problem for the downstream processor? Yeah, it would be. We're not planning to vertically integrate into servicing. We just want to provide the upfront hardware solution to enable all the servicing to be much more efficient. But yeah, it's essentially in terms of how, what happens if things go into the waste that are not supposed to be there. I mean, we're actually wondering what's going to happen when we put these as public toilets in Santa Fe. We're expecting, so we've tested for syringes, not syringes, we tested for lit cigarettes and joints. There's no issue with the membrane. But yeah, syringes, I'm curious. I mean, I think you'd have to get the aim just right and like enough force to really puncture the membrane, but we'll have to see. I don't want to over-engineer this until we see what the problem really looks like on the ground. But yeah, I mean, I think, yeah, there are also other, like, sort of geographies where people normally use toilets as trash cans, and so we'll have to see how that goes. But I can't solve all the problems, but we'll have to see what happens. Oh, sorry, yeah.
Just a question about, have you looked at like how current in-wall toilets work? Where they put all this behind the wall, so they just have the throne sort of there?
Yeah, that's kind of what we were thinking about for like a receiving tank. So in that case, I think it would be harder to get the separation unless you integrated a diverter into the.
Can you, and this gets a little maybe
Mhm.
afterwards, I put a bunch of those in, I'm looking at things like I often do like inline fans and bring 3 or 4 fans and houses together to get proper ventilation and insulation. So if this is in wall, you can push some of that solid out to somewhere, and then,
Right. So I think that, yeah.
There's no water in it. Are you still falling into like a plumbing code, or are you under?
I think they're gonna. Okay, so the question was if sorry, there were a couple questions in there.
In-wall design, like, is a way to do this.
Yeah. Have we looked at an in-wall design? So, I mean, we're still early in the sort of evolution of this product. I mean, originally where we thought the first adopter markets would be were where the alternative to our toilet was no toilet. So we didn't sort of think of a regime where, oh, you're replacing or retrofitting a flush toilet. But sort of the answer to what would you do to like essentially accommodate somebody who wants to have like a ceramic toilet, but then our technology would be to be a receiving tank or something, some kind of thing behind the toilet, maybe under the toilet. If it was under the toilet, it would be easier, but behind the toilet requires some kind of conveyance from the toilet to the system. So we haven't figured that out yet. I mean, there might be some approaches we can do, but I mean, below is easiest just because gravity helps, as opposed to pumping or, a conveyor belt or whatever. But yeah, so we have to, I mean, and we'd be happy to partner with people who are smarter than us who can help us figure that stuff out. I mean, the way an airplane does it was with a vacuum. That's one option. We haven't solved all those problems yet. So I think, but yeah, so I think the sort of, to think about doing this as a septic system, we need to figure out kind of, I mean, if we're trying to be like a low flush system, I mean, I think with a septic system, you could still have like a low flush solution, and then that just becomes extra water that you're evaporating. I think, depending on the size of the household, you're probably still within the specs of what, because we're assuming a household of 10 people where everybody uses it 5 times a day. I think that's bigger than your typical like Cape Cod family. So we might be fine if we had some extra water as flush. And then in that case, yeah, you're still using water for flushing, but on the plus is that we're returning that to the environment as pure water vapor, so it doesn't go into a sewage treatment plant as wastewater. It's just going back into the air as molecular water. So I think we could probably tolerate that from a sustainability standpoint. Yeah.
Have you looked at any agricultural applications?
Okay, so which kind of agricultural applications are you talking about? Oh, you mean to dry the manure from farm animals? So large volumes requires a lot of sort of redesign and engineering, because really what we're doing is we're engineering surface area and airflow. So if you're trying to do large volumes, you need to redesign the system to pack in a lot of surface area and airflow into a system to receive a high volume of waste. We do have actually a concepted on paper idea for a packaged sewage treatment plant. I think this is a long time ago that I came up with this. It was like 10,000 liters per day. We haven't tested if it works. I mean, we spent a full year on this design, essentially doing airflow simulations on, the computer, and then like building duct tape and cardboard versions of those designs to test how efficient they are at evaporation. So we'd have to go back into R&D mode to essentially look at a high volume, high throughput application. But yeah, so we have thought of other things like also wastewater treatment for recalcitrant waste streams. So essentially you have waste streams with pharmaceutical additives, or the brine output from reverse osmosis, or things that are actually really hard to treat with the legacy technologies like reverse osmosis, other types of desalination, or membrane bioreactor treatments. And this would be a zero discharge alternative that more efficiently addresses what are called recalcitrant wastewater streams, things with small molecules. Those are things that don't get treated by the existing systems. So there's a place for that in industrial wastewater treatment, and we'll get there. But yeah, as a startup, you only have so much rope where you can develop, and so the trick is for us to get this on the market and get people to understand it, because nobody has ever thought of this as a pathway to a solution before.
Can you just give me an idea of the scale of the bag
Yeah.
in there? Because you have this big box that you've got there, and somebody is dealing with 50
Yeah.
uses a day, and how often does it have to get changed out?
Right. So okay. So the way that this works, there's two bags. There's one for the solid where gravity helps you, and one with liquid where there's a diverter and a urinal that feeds into them. They're about 50 liters and they're shallow, so they're kind of like that big. And we're only changing them out once in 4 months. So they're getting, 20 to 50 uses per day, and then running for, 3 to 4 months before we have to change them. Oh, actually, I think you'd been, yeah.
But so when you're pointing to that, that's a 50 use per day type of system.
Mm-hmm.
Would it be smaller if it were just an individual?
Probably, yeah. Yeah.
How much smaller?
Maybe one of those maybe like approximately one of those modules, but we'd still want to figure out how to separate the liquid and the solid. But yeah, I'd say one of those modules maybe. I don't know. Yeah. Yeah, that's what. Yeah, I think that would be. I'm just spitballing it, but yeah. Sorry, there were like I think you had your hand up, and then 3 more minutes. 3 questions. So 1, there was somebody. 2, did you have a question? And then 3, did anybody else? Did I miss anybody?
Can I make an announcement at the end?
Okay, yeah, sure. So I guess all right, so yeah.
It seems the heart of your system is these magic bags.
Magic bags, yes. That's a scientific term.
Can you tell us where you source the raw materials for these? And if you looked into if this was wide-scale production, would there be any hurdles in creating a great number of these? In other words, do you have the production efficiencies you need to make this a large-scale implementation?
We're pretty much mostly there with the bags. So we have we partner with a large film extruder in the Midwest, and we've worked out how to actually make the film at scale with no faults in it. So the first time we did it, we ended up with a film that had pinholes in it, and that's defeats the purpose, because you want a non-porous layer. So we worked out how to do that. So we've patented the bag, but there's also some know-how in how to make it at scale without any flaws. So that's been scaled up. The thing that we have to scale up now is the box. So, and there's kind of two ways that we expect the box to get out. One is, sort of the outsourced IKEA version, where we work with, like in this case, we sent the CAD designs to the construction firm in Panama. They sourced the panels and the frames, they put it together, and we came down with the electronics and the bags. And the other one is like an injection molded thing that basically is like a, unified form factor. And so, by us being able, so the out licensing, I think, especially for other countries, they'll be able to source from their already existing distribution channels at scale and, in their own currency. So it'll be cheaper. And then the injection molded form should bring the cost of making these significantly down, because the biggest cost input into our systems right now is the time for my engineers. So it's the human resource part for the building the system.
Are those raw materials sourced inside or outside the United States?
Well, so I think the ones we're building for New Mexico, there's inside, or probably some parts of it from China. But outside, I think all of those materials were sourced in Central America. Yeah. I think, yeah.
What other parts need maintenance, maybe quarterly, yearly, fans, sensors, things like that?
We haven't, so these have been out for 2 years. After about a year, actually, they've been out for 3 years, and they were sitting there in kind of the tropical environment for a year before we started running them. So sort of like 8 months into the pilot, so a year and 8 months in, probably had to redo some of the electronic connections because they hadn't been properly weatherized. We're updating and sort of hardening the electronics so that they're A, weatherized, and B, like kind of idiot-proof to install and service. So we expect that with that, we shouldn't have to be maintaining the electronics, especially if you're not in an extreme environment. The fan has been running. We haven't had any issue with the fan. It's just mostly the load cells. So, and not all the systems need to have load cells. The load cells are a way that we can remotely track the data on how much waste is going into the system and how it's evaporating out. So I don't know if that answers the question, but we've hardened a lot of it too. I mean, the kids in that picture, so the super fun thing was that when we installed those kids were out of school for 1.5 years because the school was closed because the teachers wouldn't come and teach because the bathrooms were atrocious at the school. So, lack of sanitation is also an education problem in a lot of parts of the world. And so these kids you wouldn't believe it, but they were super curious. And so eventually we had to lock the back servicing doors. Like, why anybody would want to go in and see what was inside the toilet is beyond me. But we had to lock the servicing doors. We had to pretty much replace a ton of the mechanical, like the toilet seat broke a couple of times. So yeah, I think but I think we've made it more abuse proof. So assuming none of you will do that and none of you are curious about what's inside the toilet, we should be fine. But yeah, we've hardened the product through a number of iterations in the field, thanks to those children. So yeah.
I was just wondering if you could speak to the evaporation process.
What specifically?
I'm just trying to get an idea of what's going on in there.
So I think okay, so the question was to just clarify more about how the evaporation works. Okay, so maybe the best, do any of you have dry fit sportswear when you work out? Okay, so that's a fabric that takes liquid sweat off your skin, pulls it through the material, and it comes out as vapor, right? It doesn't come out as liquid, it comes out as vapor. So there are lots of breathable materials that essentially will, when they come into contact with liquid, will soak it up and pull it through the material. And then when it comes out on the other side, they're just individual molecules. They come out as vapor. So the trick with this material is that it's non-porous. So it's not a fabric, obviously. It's a non-porous layer that likes water. So there are lots of things that will soak up water. Now, like I could make an analogy to diapers, which soak up water, but then the problem with the material in diapers is that it soaks up water and it locks it in. It takes a lot of energy to release the water because the material in a diaper is very what's called hydrophilic, right? It loves water and it grabs onto it. So it's a favorable interaction for it to soak up the water. It's unfavorable for it to release the water. These are more hygroscopic, so this material. So what it does is it takes in the water, and then sort of the molecular matrix inside the material allows the water to come in and then just kind of like make its way through from the wetter side to the drier side. That's just pure diffusion as well. Molecules like to go from an area of high concentration to an area of low concentration. And so you have one side of the bag that has the waste in it, that's the wetter side, and then you have the side that just is exposed to air, and that's the drier side. Plus you're also ventilating the air past those surfaces, so you're always getting rid of the humidity that's coming through. So the wicking of the air across the outer surface is helping so that when it gets soaked up into the matrix of the membrane, it statistically wants to go to the drier side. It doesn't statistically want to go back into the wetter side. It's basically diffusion. So it's just moisture diffusion, but the membrane. And you'll get evaporation, just natural evaporation off the top surface of the waste, obviously. But because we can essentially activate 3 dimensions for evaporation, not just the top surface, but the sides and the bottom, we get about 2/3 of the evaporation coming through the material of the bag, and 1/3 coming off the surface of the waste, the open surface of the waste. You look confused still. It's just diffusion for the most. I mean, generally, if you put a puddle of water anywhere, you'll get eventually evaporation, escape of water molecules off the surface, but it's only the one surface, the top surface, right? Whereas we're allowing evaporation to happen in all dimensions, and that turbocharges the evaporation.
Okay, I mean, I guess.
So, and it's
Is it like a 2-layer kind of bag, one side hydrophilic, one side hydrophobic, or like?
No, it's a composite, but it's one. So actually you can see it's like evaporated if you guys want to come play with it, you can. But it's a composite, right? But it has this property of wanting to soak up the water. And so what you saw when I put the liquid water on here is it swelled where the liquid water touched it, like it basically went into the matrix of the membrane, and then it wants to come out. I mean, in this case, if you only have you don't have a bag of water, so it's not like, so if I put liquid water, it's probably evaporating from both sides. But in the case of the toilet, you have liquid on the inside and dry air, largely dry air on the outside. So it's that differential. So essentially that's how diffusion would work, moisture diffusion. And lots of materials have this property of moisture diffusion, but we've tuned this to have a number of desirable properties for our application. Yeah.
All right, gotta call it's 9 o'clock. So,
okay.
Diana, thank you so much for being here.